Welcome to Introduction to the Altera Agilex 5 FPGA Enhanced DSP with AI Tensor Block online training. In this training, we will start with an introduction to challenges in DSP and AI, then providing the details of the Agilex 5 Variable Precision DSP blocks, Enhanced DSP with AI Tensor Block, followed by Agilex 5 DSP block performance details. Let's focus on the introduction section now. FPGAs are used in a wide variety of applications. On the left-hand side, you see several application domains. On the right-hand side, you see the type of math operations required for different applications from low to very high precision. No direct one-to-one mapping exists between the application domains on the left and the precision required on the right. Audio compression is likely to require much less precision than medical imaging. Radar likely requires higher precision and processing rates than video compression. Furthermore, as applications such as speech recognition, which has traditionally been done with low precision audio signal processing, migrate to being done by AI, we have other challenges. AI brings new challenges to the design community. The DSP solutions are developed whereas AI solutions are trained. To explain how this impacts design choices, let's look at an example. The Huff algorithm is a traditional DSP algorithm used for feature extraction. It requires n-squared operations, where n is the image size. An AI CNN algorithm can also do feature extraction. The number of operations required by a CNN is n-squared times L, the number of layers, times m filters per layer, and k, the filter size. Training an AI is typically faster than developing an algorithm. This means faster time to market. In an FPGA, you only implement the logic which is required. Custom logic in FPGAs is inherently more efficient. The final trend to highlight is the computational needs at the edge. An increasing amount of data is being generated at the edge. That data needs processing before going over the network. And low latency performance is typically a requirement. The amount of data being processed at the edge of today's network requires devices that can deliver on performance. The power and latency needs at the edge have not changed. Low power and low latency are required and need to be deterministic. Agilex 5 FPGAs are the only FPGA fabric infused with AI. Built on Intel 7 technology, Agilex 5E series FPGAs deliver superior power-efficient performance at 1.6x better performance per watt compared to the competing 16nm FPGAs and have the first asymmetric ARM application processor cluster to deliver better HPS energy efficiency. The efficient feature include up to 56 TOPS for INT8 DSP with AI tensor blocks, customizable AI pre-post-processing logic, supports DDR4, DDR5 and LPDDR4 and 5, multi-core ARM, YESOC A55 and A76, hardened PCIe 4.0, multiple high-speed video I/O standards, deterministic low-latency, low-power device, small package sizes, 15 by 15 mm to 23 by 23 mm. Let us understand more on the Agilex 5 Variable Precision DSP block architectures. The Agilex 5 Variable Precision DSP consists of the following blocks: 1. Fixed point arithmetic. 2. Floating point arithmetic. 3. Tensor mode block architecture. In fixed point arithmetic mode, you can configure the DSP blocks to support signal processing with precisions from 9x9 up to 54x54. The features are increased 9x9 multipliers count, with 3 9x9 multipliers for every 18x19 multiplier. A pipeline register increases the maximum DSP block operating frequency and reduces the power consumption. Dynamically switch multiplier inputs through scan-in and chain-out signals. The FP32 single precision floating point arithmetic DSP can perform the following modes: FP32 multiplication, FP32 addition or subtraction, FP32 multiplication with addition or subtraction, FP32 multiplication with accumulation, FP32 vector 1, FP32 vector 2. Multiplication mode allows you to apply basic floating point multiplication equation. Result is the multiplication of two given inputs. The floating point multiplication mode supports the following exception flags: invalid, inexact, overflow, or underflow. Adder or subtractor mode allows to perform addition or subtraction of the given inputs. The floating point adder or subtract mode supports the following exception flags: invalid, inexact, overflow, and underflow. The tensor mode high-level block diagram is shown in the figure. In tensor mode, there are two dot engines and ALUs arranged as two columns. The dot engine computes the fixed point product of 10 individual 8-bit data inputs and 10 preloaded 8-bit buffers, and sums all of the results together. A load buffer select signal controls which set of weight is active. This allows one set to be updated while the other set is being used for computations. The dot product outputs from each column are fed into independent ALUs. Let us understand more about AI tensor block and tensor mode in this section of the training. In the tensor block, each column has 10 multipliers, so that is 20 8 multiplications happening at the same time across the block. These multipliers are working on 8-bit integer data, and their outputs are fed into a summing unit, where they're combined to get the dot product for each column. Once the dot product is calculated, it gets converted from fixed point to FP32, so we keep precision for later stages. This block can handle all 20 8 multiplications in a single cycle, making it super efficient for tasks like deep learning, where int8 data formats help speed things up without sacrificing too much precision. This block is all about balancing speed and accuracy, processing a bunch of int8 operations quickly, and then accumulating the results with FP32 precision. There are three operational modes for tensor mode: tensor floating point mode, tensor fixed point mode, tensor accumulation mode. Let us discuss them one by one in the upcoming slides. In the tensor floating point mode, the dot engine feeds the arithmetic logic unit, which operates in floating point mode. A shared exponent is supplied with the input data, and separate shared exponents are loaded into the two sets of ping-pong buffers. These shared exponents are used in the arithmetic logic unit to perform a fixed point to floating point conversion. It represents and manipulates rational numbers and operates in the floating point format, which is IEEE 754 standard. In the tensor fixed point mode, the dot engine feeds the arithmetic logic unit, which operates in fixed point mode. It represents and manipulates integers and fixed point numbers. In tensor accumulation mode, the dot engine is bypassed and arithmetic and logic unit operates in floating point mode. A 32-bit floating point input is supplied directly to the arithmetic and logic unit for each column. It represents and manipulates rational numbers and operates in the floating point format. In all three operational modes, the arithmetic logic unit features an accumulator and cascades signals between DSP blocks. In the modes where the dot engine is used, weights are preloaded into two sets of ping-pong buffers that can be selected during computation using the load buff_cell signal. There are two different methods for preloading the weights: data input feed preloading method, side input feed preloading method. The data input feed preloading method preloads the 10 8-bit weights data and 8-bit shared exponent data into the ping-pong buffers using data_in and shared exponent data buses. The weights and shared exponents data can be preloaded into the ping-pong buffers parallelly and independently. It takes 2 cycles to load one set of ping-pong buffers or 4 cycles to preload all 2 columns into the 2 sets of ping-pong buffers. Data computation is not allowed during the weights and shared exponents data preloading because this method uses all the block input bandwidth. The figure in the slide provides the concept of data input feed preloading method. Let us understand the timing diagram of the data input feeding method. C1 refers to buffer load for column 1, and C2 refers to buffer load for column 2. In cycle 1 to 2, load_BB_1 is equal to 1 and load_BB_2 is equal to 0 to preload the weight and shared exponent data into the first set of ping-pong buffers. The data and shared exponents are loaded in the ping-pong buffers for column 2 in cycle 2 and for column 1 in cycle 3. In cycle 3 to 4, load_BB_1 is set to 0 and load_BB_2 is set to 1 to preload the weight and shared exponent data into the second ping-pong buffer. From cycle 6 onwards, the load_BB_1 and load_BB_2 signals are set to 0 to disable the weight and shared exponent data loading. The side input feed preloading method preloads the 10 8-bit weight data and 8-bit shared exponent data into the ping-pong buffers using side_in_1 and side_in_2 8-bit buses. The preloading process takes 12 cycles to complete preloading for one set of ping-pong buffers. The weight and shared exponent data are preloaded independently even if the DSP blocks are cascaded. This enables the tensor computation to continue using one set of buffers whilst the other set is being preloaded. Let us understand the timing diagram of side input feeding method. SEC1 refers to the shared exponent for column 1, and SEC2 refers to the shared exponent for column 2. BXCY refers to the buffer associated with data _in_x in column Y. That is, B10C2 is the buffer multiplied with data _in_10 in column 2. The process is divided into 3 steps. In step 1, the update process starts in cycle 1 by setting load _BB_1 or load _BB_2 to 1. In step 2, new shared exponents and weights are loaded during cycles 2 through to cycle 13. In step 3, that is in cycle 14, the newly loaded buffer content is ready for computation, and the load _buff_cell signal can be switched to the new buffer set for computation to continue with the previous set. Let's get into the Agilex 5 DSP block performance numbers now. Let us understand how Altera FPGAs use block floating point or BFP to get the best of both worlds: high AI accuracy and compute efficiency. Block floating point or BFP is a method used to provide an arithmetic approaching floating point while using a fixed point processor during inference. The FPGA takes floating point data and converts it to block floating point. Block floating point uses smaller bit widths, but still delivers near floating point precision, so it's all about efficiency. With BFP, we can get the same accuracy as traditional floating point models, but with over 50% smaller models. In summary, Altera FPGAs with BFP give you smaller, more efficient models, while still maintaining almost perfect accuracy. The supported list of BFP numerical precisions are shown in the table. For INT9 BFP and INT8 BFP, 2's complement is used rather than sign plus magnitude, so there is no sign bit required. There were 2 major innovations for Agilex 5 in the AI tensor block. One, it has been designed specifically to focus on efficient data movement patterns like computational patterns relevant to matrix and vector multiplication workloads. It does efficient functions like convolution and linear regressions commonly used in AI. 2. A new block floating point numerical format is introduced, block FP16, and it can be configured to support int8 also. This allows for maintaining the flexibility of floating point formats while maximizing the power and area efficiency of the AI tensor block. In Agilex 5, DSP block is enhanced with a new tensor mode architecture, which increases the number of multipliers to 20 up to 5x compared to other Agilex families. Let us explore the Agilex DSP block precision support summary. Agilex 5 can do 20 INT8 multiplication operations per clock cycle in tensor block mode, while Agilex 7 can do only 4 INT8 multiplications per clock cycle but no tensor mode supported. So Agilex 5 INT8 shows 5x improved compute density. They offer an order of magnitude improvement in AI and DSP compute density. INT9 shows a 50% improvement, and the 16-bit complex multiplier shows a 2x improvement. These are mainly used for signal processing, although Agilex 5 has more compute density than Agilex 7 per DSP block. Agilex 7 M series has more overall compute power than Agilex 5 due to the sheer number of DSP blocks available. You can refer to the resources listed in this slide to get more details. The resources are available for both Agilex 5 devices as well as for the FPGA AI suite. In this training, we have discussed about the variable precision digital signal processing blocks in the Agilex 5 devices, which can support fixed point arithmetic, single precision, half precision floating point arithmetic, and tensor-based operations. Key details of the Agilex DSP with AI performance are up to 56 TOPS for INT8, 56x improvement over Cyclone 5 FPGAs, 4x improvement over Aria 10 FPGAs, 2x improvement over Stratix 10 FPGAs, abundant DSP processing power, up to 3680, 18 by 19 multiplications per device, or up to 5520, 9 by 9 multiplications per device. The FPGA technical training team is always looking to improve our material and welcome any feedback you may have. Please email to fpgatraining@intel.com with any of your thoughts or comments. Thank you.